Okay, so Unit 4, Assignment 4, Task 2 is for the distinction Part 1. If we look at this task, it's to investigate a voltage across a smoothing capacitor and a resistor. And you will have done this sort of thing in your electronics course. You'll have looked at a capacitor and a resistor in a circuit. You're given some information about the circuit. The value of the capacitance is 100 nanofarads. The resistance is 47 kiloohms. And the initial voltage that's applied across the capacitor is 5 volts. So already there's an issue around units there when you come in to put the values into the... You know, I hope, that that's the shape of the curve that you're going to get. You're given the function that you're going to describe. V equals V naught, that's this function here. V equals V naught, 1 minus e to the t over tau. V equals V naught, 1 minus e to the t over tau. V function, the notation Vt is used. And that's this curve. I've not plotted the exact curve here, but that's the shape of the curve. It's an exponential growth to a limit. And it's describing how the voltage will vary across the capacitor in a circuit. So if I were to sketch this circuit, I'd have a resistor in the circuit, a capacitor in the circuit, and some sort of voltage applied, a 5-volt DC voltage applied. And what we're looking at here is the voltage across the capacitor. Now, if you think about it, this circuit from the electronics point of view, or from the way a capacitor works, the initial resistor of a capacitor is 0 because there's no charge on it. So the instant I turn on the circuit, put the voltage across, there's going to be no voltage across the capacitor because there's no resistance. And that's this point here on the graph. And then as time goes by, charge is going to build up on the capacitor, so it's going to resist the flow of charge, and the voltage will gradually increase. And that's what's going on here. Until you get to a steady state. What will that maximum voltage be across the capacitor eventually? Given that this is the initial voltage, 5 volts. What will be the voltage across the capacitor eventually? 5 volts, right, because eventually all the voltage will be across the capacitor because the resistance will be virtually infinite, so there will be no voltage remaining for the resistor. So at the end of the charging cycle, what will the voltage be across the resistor? Oh, naught. Yeah, all the voltage will be across the capacitor, none across the resistor. So as time goes from 0 onwards in this direction, the voltage across the capacitor will be building to a maximum voltage, but the voltage across the resistor will be starting at 5 and then falling. Okay, that's the sort of the physics behind this situation. What's going on in this circuit? And I think it's something you've been talking about already in your electronics. Yeah, this sort of thing. This question then is about investigating that. If we look at the task, it says calculate the time constant for the circuit for the first part. Well, you're given the formula for the time constant. So this symbol here, which incidentally is called tau, T-A-U, represents the time constant for the circuit. Calculate it, there's the formula. Use graph plotting software, autograph in other words, to plot the charging curve over the range 0 to 20 milliseconds. So you've got to plug in the formula, put in the values, and then get autograph to show the curve over 20 millisecond period, from 0 to 20 milliseconds. When you've done that, there's a bit of, for part C here, internet research is required here to investigate how the time constant can be estimated. So you need to look up the time constant in these things if you've not already done it in your electronics. And from that investigation, you'll see how you can use your graph to estimate a value for the time constant. So then from the graph you've plotted in part B, you can then confirm, hopefully, the calculated value for the time constant that you calculated here. So that's part C. Fairly straightforward so far. Part D, differentiate the function with respect to time, and that will give us a new function which tells us the rate of change of this function. It tells us the gradient of this curve at different points. Okay? So what you've got to do in the task then is to differentiate it. Part E, use this differential function to find the rate of change of the voltage at 6 milliseconds. So you go to 6 milliseconds on the curve, wherever that will be. If it was here, what's the gradient at that point? It won't be there on your graph because it will be a different graph. Might be around here somewhere. So what's the gradient at that point? And then, once you've done that, the idea of the rest of the question is to use autograph to try and find the gradient at 6 milliseconds and then compare your answers. That's the last part. So if you've got the graph of this function here, and let's say this was the point, I can estimate it by drawing a little triangle around that point and finding the gradient by dividing y by x. So there's a bit of internet investigation involved with this, and a bit of thought and getting familiar with the way the autograph software works. Okay, so that's that distinction question, part A of that. And then task 3 asks you then to go a bit further to investigate how the voltage across the resistor in the same circuit will behave. And we've talked about that briefly already. Think back to what I was saying at the start about this circuit here. So now you've got to consider the voltage across the resistor in the circuit and do a similar thing. Use differential calculus to find the rate of change of the voltage when t equals tau, the time constant. And then again use graph plotting software to confirm this rate of change. So similar to the first task, task 2. Quite involved. It does take some time to do and a bit of internet research, familiarity with autograph. So you'd expect that it's a distinction question. Okay?